used. So let us have a look at how the schematic would be for a 12 segment or 12 coil machine. So we continue to have the north and the south pole, the north and the south pole. Let us have a reasonably bigger diameter circle here, and we have the commutator which is now having 12 segments. The brushes mounted on the neutral zone, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have the commutator. There should be 12 slots on the core, the rotating shaft, as shown here. And these 12 slots, you need to have 2 coils out of phase with each other. So you will have 2 coils out of phase with each other. So we will have 12 coils which are connected in the following. So let us put the schematic. So coil 1, coil side 1 and 2. So each coil is having 2 sides which are the there on diametrically opposite ends of the core. So let us say this is coil 1 coil, then the let us say A dash, and then another coil is connected in this fashion. So like that you have 12 coils which are connected. So at the given at a given point of time, the picture here, let us see the voltage. The voltage across this is going to be 0 volts because this is at an orthogonal axis with respect to the north-south axis. The voltage here is going to be 0 volts. The voltage here could be probably, let us say, 10 volts. the voltage here is going to be 10 volts. Let us say the voltage here is 8 volts and the voltage here is 5 volts. The voltage here is 8 volts, 5 volts. So you have 5 volts, 8 volts, 10 volts, 8 volts, 5 volts, symmetrically distributed. The voltage across the brush. So the voltage across the brush, let me bring out the brush leads outside here. The voltage across the brush, let us say this is positive and this is the negative, is, you see that all these conductors, all these segments are connected through the coils. So between 2 and 3 you have 5 volts, 3 and 4 you have 8 volts, 4 and 5 you have 10 volts, 5 and 6 you have 8 volts, 6 and 7 you have 5 volts, and then between 7 and 8 0 volts. So across the brush it is summation of this 5 volt coil plus 8 volt coil, 10 volt, 8 volt, 5 volt. So that would lead to 16 plus 10, 26, 36. So that will be 36 volts at this particular point. So you will see that the ripple here will be much lesser than in the case of the 4 coil DC machine. Now just imagine that what would happen. So the brushes are no longer here, but instead the brushes are connected to these points. Now you see that the voltage across the brush now is between 3 and 4 you have 8 volts plus 10 volts plus 8 volts, that is 26 volts, plus another 5 volts, which is now 31 volts for this brush position, which means the voltage across the brushes is going to be going to reduce, and further the brushes are shorting the 5 volts across the coil. In the earlier position, when it was 0 volts, when it was kept at the orthogonal position in the neutral zone, at that position any coil at that position would have 0 volts, and therefore it will not, brush will not short the coil, and even if it short there is no circulating current. Here, because the brush is not in the neutral zone, at the point where the commutator segments change over, the coils are shorted. So the coil around at that point the induced voltage across the coil is around 5 volts, which means the 5 volts get shorted to the through the 2 commutator segments because of the brush. So it gets shorted through the brush here. So which means there can be huge circulating currents in the coil winding, which could result in a lot of I2R losses. So this is how the DC machine will look like, and the structure of the DC machine is in this fashion. At this point, it may be a good idea to have a look at how a real motor, the core of a real motor, the shaft of a real motor will look. So let us have a look at the shaft. Before that, I would like to put in. These are called the poles. These, as you know, are called the commutator segment. These are brushes. Now these are the coils, and it is called the armature coils. armature coils. This whole thing is the rotor. The whole thing is the rotor which is rotating about a central axis. Now let us the real motor or real rotor, how it looks like. Let us have a look at this rotor. This is the rotor of a DC machine. This portion, what you are seeing, is the commutator segment. This is again a 12 segment commutator. You have 12 slots on the rotor. These are the rotor slots through which the coils are wound, and there are 12 coils. So the coils here are coming from the slots, from the 12 slots on the rotor, and you have the commutator segments. The coils are soldered onto the commutator segments here. If you notice, the coils are soldered onto in the winding fashion that we just discussed. This type of winding fashion is called the lap winding. Now this whole rotor will be mounted onto a central shaft, and then above that one will be another enclosure called the stator, which will have the poles and the north and the south poles. It could have more than one set of poles, and that would make the complete machine. This whole set together is called the armature. So the armature consists of the core, and that is also laminated here, again because as we were explaining during the time of the transformers, the laminations are used to reduce the eddy current losses. This portion is the coil ends which are joined to the commutator segments. The brushes will come in contact at this copper surface of the commutator segments. So the brushes will come in contact like that. It will be spring loaded. We will have a look at that in a different machine. You see that this is the armature which is fully mounted onto a yoke, and this is a complete motor which you see here. The shaft is capable of rotating here. So when the shaft rotates, the commutator segments here, which are the coppery portions, make contact with the brushes. There are two brushes here on these two sides, and the commutator segments make contact with the copper coils by virtue of being soldered. Now at this end there are very fine solder joints which make connection with the coils inside on the rotor, and this is a 38 slot motor, and therefore you have much less ripple as compared to a 2-pole, as compared to a 2-slot or a 4-slot motor that we just saw. 4-slot meaning you have 4 slots on the rotor with 4 coils. 12 slots means 12 coils. 38 slots means you have 38 coils in this here. So coming back onto the board, we now saw the structure of the DC machine. And in the case of the DC generator, the power comes from the shaft. This is the shaft, the mechanical shaft, which is in the mechanical domain, enters the DC machine This is the DC machine, goes through the magnetic domain and through the brushes, the power is fed to the external electrical circuit through which to which the terminals of which is the load. It could be some load or it could be a load impedance. Okay, we will come to that. So, this is a schematic of the whole DC machine, and we were looking at the internals of the DC machine, how it is structured and how mechanical rotation can give rise to a voltage, and that to a unidirectional voltage or a DC voltage. So, if we have many slots, many coils per pole, then the voltage across the load, the induced voltage across the load will be almost ripple free. It will have negligible ripple across the load. And now, let us look at how much voltage is induced across the brushes. The induced voltage, we will call this one as E generated. E generated is given by N phi Z by 60, where N is the RPM of the shaft rotation or the rotor rotation. RPM is revolution per minute, revolution per minute. And phi is the flux per pole. This is in Webers. Notice that we have always put one pole set, one north pole, one south pole in all our discussions till now, but it is not necessary that it should be just one pole set, there could be many pole sets. So, the flux phi is the flux per pole, and Z is the total number of conductors on the armature, is the total number of conductors in the armature. So, the total number of conductors in the armature, the flux per pole and the speed at which the rotor is rotating, they are linked to the value of the induced voltage or the generated voltage. So, the generated voltage Eg is actually derivable from the alternate Faraday's law of electromagnetics. The equation which we have been using in the DC machines, E which is equal to B L V, where B here is the flux density, this is the length of the conductor, and this is the speed at which the conductor is moving, and this is given in meters per second. And from this we have arrived at the induced or the generated EMF Eg, which is N phi Z by 60. Now, N is the rotation revolutions per minute, rotation of the rotor. So, rotation speed of rotation of the conductors. So, this is related to the V, velocity there. The number of conductors is related to the length of the conductors and the number of turns in the coil. And then the flux, of course, is related to the B. So, starting from this equation, E is equal to BLV, the Faraday's equation or from the law of electromagnetics, one can derive this equation. Now, let us consolidate this understanding of this equation with a simple example, which will give us a better idea of using the equation. So, let us consider a DC machine whose armature has 6 poles. And the speed at which the armature is going to rotate will be 600 revolutions per minute. Now, this machine is designed to have 90 slots. By slots, you see we were writing these slots, you remember, on the surface of the core, on the surface of the circular core. So, this was a 4-slot machine. Like that, let us say you have 90 slots, and each coil, the coil that is wound through the slots, has 4 turns per coil. That is, we used to always draw a coil with just 1 turn, but there could be many more turns than 1, and in this case this particular generator is wound with 4 turns. And the flux phi, which is 0.04 Webers, is the flux per pole. So, when given these information, what is EG? The generated voltage or the generated EMF. So, EG is N phi Z by 60. So, let us first calculate Z, total number of conductors in the armature. So, there are 90 slots, therefore, there are 90 coils, and there are 4 turns per coil, and 2 conductors per turn. For every turn, there are 2 conductors which are diametrically opposite, 2 coil ends basically. So, this means this equals 90 into 4 into 2, which is 720 total number of conductors. The speed N is 600 RPM, and therefore, EG is 720 into 600 RPM into 0.04 Webers flux per pole divided by 60, which is equal to 288 volts. This will be the induced EMF across the brushes of the generator of this particular DC machine, which has a specification as given here. Now, we know how to calculate the induced EMF across the generator. We need to look at the circuit of a generator and also the state equation that you would obtain for the following generator. The general state equation, that is in the form x dot is equal to x plus bu, y is equal to cx plus du, so that you can do any analysis on any type of generator, because all generators, DC generators, fall under the similar constructional principles and operational principles, and thereby they can be mathematically modeled. We will look at the mathematical model of the DC machine, DC generator. We shall also look at the voltage regulation characteristics of the DC generator and the different types of excitation, that is how the pole or the flux is produced within the generator. And another important issue, and that is on the armature reaction, a concept which we have still not discussed, but we will discuss in the following session, the concept of armature reaction and how it is it can be avoided. Now, all these issues we will be discussing in the coming session. In this session, I would like to point out that the operation principle of the DC machine is quite simple actually, and the number of coils, the number of slots are increased so that you get a twofold advantage. One is the increase in voltage across the brushes, because each coil between the brushes there are now going to be more number of coils, and therefore the induced voltages of all these coils are going to add up and then come across the brush voltage, as we saw in the discussion today. And the second, the more important thing is that the voltage across the brush will have very less amount of the ripple as the number of coils and the slots increases. So these two are the primary advantages in having large number of coils. Further, if the number of poles are also increased, then the ripple content in the DC machine, in the output of the DC machine will be negligibly small. So we shall continue in the next class trying to consolidate on the mathematical model of the DC machine.